Good morning, everyone. Today we are going to study an important topic called scheduling policies in operating system. Right? Before that, just we'll have a quick revision what we have discussed in the last class. Now, in the last class, we tried to understand how operating system run a process. We tried to understand the mechanism of how the operating system run a process, and then we also try to understand the mechanism how the operating system handles a system call, and then we discussed what happens when we make a move from one process to the other process. That we call it as context switch, right? So we know that to create a process, first the memory is allocated by the process, by the operating system. The memory is allocated for the process by the operating system, and it creates the memory image. The memory image consists of code, data, stack, and heap. This is the first thing the operating system does. The second thing what it does is you have a CPU. In the CPU, you have multiple registers. So this registers will be set up next by the operating system, that is program counter, data register, and then stack pointer. So after all of these setups, the operating system is just out of the way, and then the process directly run on the CPU, right? And we know that when we make a function call, so you have a code, data, stack, and heap of the memory image. So when in the code, when you make a function call, in the stack we store the old PC value, right? Just to go back, uh, just to go back to where it is stopped, the execution, right? That is the reason why we store the old PC value in the stack, right? And we also discussed about a system call. So you have a CPU, you have an user mode, you have a kernel mode. Now in the user mode, you have a memory image of a process. In the code segment, in the code, when you invoke a system call, then the CPU move from user mode to the kernel mode, right? So because when the CPU move to the kernel mode, it will have higher privilege, right? All of your system calls, the code for the system calls, all available in the operating system mode. That is why the CPU move from user mode to the kernel mode to execute the instructions related to the system call, right? And when CPU move to the kernel mode, it does not trust the user to provide the address, right? So let's say that you have multiple system calls. To read a data from the disk, you have one system call. To write a data to the disk, you have another system call. So all of these system call instructions will be stored in IDT, interrupt descriptor table. Now each system call have a separate address in the IDT table, and the kernel will not trust the user to provide the address of the system call, right? Instead of that, the CPU have an interrupt descriptor table. No, it has an address of all the system calls. Therefore, whenever the CPU move to the kernel mode, it will go to this IDT table and look the addresses, and then it will execute those, right? And then we discussed about the mechanism of trap instruction. That is, when we make a system call, the special trap instruction is executed. Therefore, the CPU move from move from user mode to the kernel mode. Therefore, it has higher privilege level, right? So when we move CPU from user mode to the kernel mode, we always switch to kernel stack, right? And you save all the PC value registers in the stack. After the execution of system call instruction, we have to go back to the user mode and start the execution where you stopped, right? So in order to go back, we store the old PC registers and so on, right? And we also discussed about what are the different scenario where the trap instruction is executed. One is when you're invoking system call, other one is when the program fault occurs, and when the interrupt happens. So these are the three different cases where the trap instruction will be executed, right? Now, once you come to the kernel mode, once the CPU comes to the kernel mode for the execution of system call or for the execution of operating system code, how it goes back to the user program, how it goes back to the user mode.
Using return from trap instruction.
Good, good, very good. We have to run a special instruction written from trap, right? Fine. So when the CPU move from the kernel mode to the user mode, uh, we no need to go back to the same process. The operating system decides whether to go back to the same process or can I move to different process in the user mode, right? Now we know that why a switch between the process. Once you are in the kernel mode, when the CPU in the kernel mode, the operating system decides whether to go back to the same process in the user mode or not. Now, what are the different cases? Why it will not go back to the same process? The one is the process may be exited or may be terminated, right? The process is no longer available in the user mode. In that case, the operating system will not go from the kernel mode to the uh, same process in the user mode. The second case is when the process made a blocking system call. Now, what do you mean by blocking system call here? The process is waiting for some, the process has requested for the operating system to do some job, right? The process may need some data from the disk, so it has issued the request. Therefore, the process is blocked. At that point of time, if the when the CPU in the kernel mode, it will not go to the process which is blocked, right? And there are other cases, the operating system do not want to return back to the same process if the process have utilized the CPU for the longer period of time, right? Because operating system has a responsibility to time share the CPU among the multiple processes, right? So in all of these cases, the operating system performs a contact switch, right, from one process to the other process. Now we know that the operating system scheduler have two important parts, policy and mechanisms, and we also discussed about non-preemptive. Uh, what do you mean by non-preemptive?
That scheduler which actually a switch between the processes when the process is actually terminated.
Okay, so you have multiple process in the system. Okay, you have P1, P2, P3, and so on. Now the process P1 need 5 milliseconds, process P2 need 6 milliseconds. Now, in the case of non-preemptive, the CPU will execute the process P1 completely for 5 milliseconds. Only when the process P1 completes the execution, only then there will be a contact switch. Okay, only then the CPU move to the process P2. But in the case of preemptive mode, in the case of preemptive scheduler, the process P1, the total execution time for the process P1 is 5 milliseconds. In the case of preemptive, the process P1 may executed for 2 milliseconds and it is waiting for remaining 3 milliseconds. When, okay, when the process executes for 2 milliseconds, the CPU can generate interrupt. The CPU can generate timer interrupt. So when timer interrupt generates, the operating system moves CPU from process P1 to P2. Okay. All right.
Yes, sir.
Yes, sir.
Yeah, fine. And we also discussed about the contact switch. Uh, so let us recall this. You have a CPU, you have a user mode, and you have a kernel mode, and you have a memory image of process A. Okay, and the same memory image of process A will also be available in the kernel mode: code, data, stack, and heap. Right. So you have a process A in the user mode, which has a memory image which consists of code, data, stack, and heap. Now, when CPU executes the instructions in the user mode, in some part of the code, the user may invoke a system call. Okay, to execute this system call, the code for this system call is available only in the kernel mode. Therefore, the CPU move to the kernel mode. When it move to the kernel mode, in the kernel stack, the CPU store the PC value of the user code, right? That is, in which line it is executed lastly, in which line it has stopped the execution. That line have an address. Okay, that line have a PC value, right? That value is stored in the stack of the kernel. Okay, now when the CPU completes the system call code in the kernel mode, then the operating system, here you have a stack pointer in the kernel mode. The stack pointer is currently pointing to the stack of the process A, right? And now the CPU moved to the kernel mode. Now the operating system want to switch to the process B. You don't want, see, you have come to the kernel mode. Now, after execution of system call code, the operating system don't want to go back to the user mode of process A. Okay, it decided, the operating system decided to switch to the process B. So the stack pointer will point to the stack of the process B. Okay, the stack pointer will point to the stack of the process B. Now inside the stack, what information you have?
Old PC value
Old
of
PC.
the user mode of the process
Which process?
B.
Good, because SP is pointing to that. Okay, initially SP was pointing to the stack of process A. After operating system decides to switch to the process B, then SP will point, the stack pointer will point to stack of process B. Now in the stack of process B, we have uh, the value of program counter, the old PC value. Now, who have restored this the old PC value of process B? You decided to switch to the process B, and who has stored this stack value of process B?
Maybe before the OS has executed process B,
Good.
at the
In
last
some,
operation it saves the content.
good. In some times in the past, before executing process A, the operating system has executed process B for some time. Okay, at that point of time, operating system may thought, I'm enough with process B. Let me go to the other process. So where it is stopped lastly, right? Where it is stopped the execution, last line, in which line it has stopped the execution, that PC value will be stored in the kernel stack of process B. Now SP is pointing to that, therefore the CPU will move to the user mode of process B and will continue the execution of code where it was stopped in the past. Okay, now when we move from kernel mode to the user mode, we run a return from trap instructions, right? Now what do you mean by context?
So the
PC and
program
other
counter and
CPU.
the CPU register.
Good, the informations related to a program counter and the CPU registers. Now what are the different scenario where we save this context? We have discussed all of this. Now what are the different scenario where we save the context?
When you
So
move from
when the
user mode, okay.
Yeah, good, please go ahead.
so when we move from the user mode to the kernel mode, and when we switch context between two processes.
Good, exactly. Now, there are two different scenarios where we save the context. One scenario is when the CPU move from user mode to the kernel mode, then we save the context. Okay. The other scenario is during the context switch. When we switch from process A to process B, at that point of time, we save the context. Okay.
Yes, sir.
Fine. Okay, good. So everyone understand this, right? In more clearly, more detailed, the mechanism of trap instruction, written from trap, contacts, contact switch. Everyone okay with this?
Yes, sir.
Yes, sir.
Yes.
Can I have a loud answer from everyone? Is that okay with you?
Yes,
Yes,
sir.
sir. Yes, sir.
Yes,
Yes,
sir.
sir.
Good, good, fine. Now we are going to discuss on scheduling policies, right? Now, what do you mean by? I think we have discussed this, right?
Yes, sir. Till optimization, you
Yeah,
said.
optimization code. So let us try to recall this. So what do you mean by scheduling policies? So in operating system scheduler, okay, in operating system we have a scheduler code. In the scheduler code we have two important part. One is policy, other one is mechanism. Now what is mechanism? What is mechanism?
Switching from one process to another process.
Good. Switching from one process to the other process. Please look at the slide. Okay, we have discussed this in last class. So in operating system scheduler code, we have two parts. Mechanism is switching from one process to the other process, and we have discussed that how the CPU or how the operating system switch from one process to the other process. Now we are going to discuss about policies, right? Now, what do you mean by policy here? When you have multiple process in a system. Now, which process you are going to select for the execution, right? That we call it as policy, right? Now, okay, like can you recall those process state transition diagram? You have ready state, you have running state, and you have block state, right? Now, what do you mean by ready state?
The process is ready to execute.
Good. In the ready state, you will have multiple process which is ready for the execution. Now we have a scheduling policy to pick one process for the execution, right? That is what we are going to discuss today. Okay. Now, uh, now in the operating system scheduler, we have something called CPU bursts. What do you mean by that?
The time required by the process to complete in a continuous stretch.
Okay, burst time is when the process comes for the execution, it runs for a continuous, certain continuous duration time in the CPU. Okay, that we call it as CPU burst. The time used by the process in a continuous stretch is called CPU burst. Okay, fine. Now, in the operating system scheduler, we have certain goals, right? Uh, that our scheduler algorithm have certain goals. The first is maximize the utilization of CPU, right? We need to make sure that the CPU is fully utilized as far as possible. Okay. The second is we need to minimize the turnaround time. What do you mean by turnaround time?
Time from process arrival to completion.
Yeah, the time the process is created and comes to the system and it completes the execution. Okay, the arrival to the completion. This time is called as turnaround time, and we want to minimize this. Okay, we don't want the process to be stayed in the white queue for the longest period of time. As soon as the process comes in, we try to make the process to complete the execution. Therefore, we reduce the turnaround time. And what do you mean by its response time?
Time from process arrival to first scheduling.
Yeah, so we want to minimize this response time. Okay, the time the process arrived and it first scheduled, that we call it as response time. And the fourth goal is fairness. The operating system is responsibility for making the CPU available for all the process equally. Okay, that is fairness. And what do you mean by overhead? Minimizing overhead.
To context switch as and when required.
See, we want to minimize this overhead. And what do you mean by this? When we make a contact switch from one process to the other process, it will take at least 1 microsecond. Now, if you do this contact switch very frequently, what happens?
A good amount of time would be consumed.
Yeah, for every contact switch, we need 1 microsecond approximately. Therefore, if you do this contact switch very frequently, then uh, no, we spend the CPU spend more time for making a contact switch. So once the operating system decided to execute a process, we have to execute the process for longer enough time. Okay, therefore we can minimize the overhead. All right. Okay. Everyone okay with this?
Yes, sir.
Yeah. So the first scheduling policy, what we call it as FIFO. FIFO. Okay. F5, F4. First in, first out. Now you have two diagrams here. Just observe the diagram. Then let me give the explanation. Okay. All right. Now if you look at figure 7.1. Okay, suppose let's say that we have three processes A, B, C arrived to the system at time t equal to 0. At time t equal to 0, we have three processes A, B, C which comes to the system in the order A, B, C. Okay, the process comes to the system at time t equal to 0 in the order A, B, C. Right now, so if you look at this figure timeline, it shows that the process A is running, followed by process B and then process C. Why is this? How this scheduling happened?
Time sharing based on the priority.
Not priority. What is the name of this policy? First in, first out. What do you mean by this?
The first process which entered will be removed first.
The process which comes first to the system will be executed. Okay, I repeat, at time t equal to 0, we have three processes in the system. Three process comes to the system at time t equal to 0 in the order A, B, C. So first A comes and then B and then C. So because it is first in, first out, the CPU will first execute process A and then process B and then process C. Okay. All right.
Yes, sir.
Sir,
Yes.
but
Yeah.
process C is at t equals 20. So like it's after 20 seconds or what?
Yeah, the process C is executed after 20 seconds. It means what? The process C has arrived at time t equal to 0. All the process has arrived at time t equal to 0, but the process B just arrived after B. The process C just arrived after process C, after process B. So the process B have to wait for the process A to complete the execution, and then B start the execution, and then C. Okay. All right.
Okay, sir.
Yeah, so as of now, you just understand how this algorithm works. Maybe in the next lecture, we'll be doing some numerical. At that point of time, you will understand how the switch happens from process A to process B. Okay. Okay, fine. So what is the problem with this policy? Conway effect. What do you mean by this? Look at the diagram 7.2. What do you understand by this?
That the first process is taking a lot of time.
Good. Sometimes, see, you have three processes A, B, C. Sometimes the process B have stuck behind the long process, the long fat process. Now, what will happen to the turnaround time of process B?
That would eventually like be greater only.
Now, the process A have took long time for completing the execution. Therefore, what happens to the turnaround time of process B? What do you mean by turnaround time?
When it comes in.
Comes in
Till completion of that process.
completion of execution. At what time process B comes to the system? For this example,
100.
Goes to 0.
time 0. Please look at this first slide.
Sorry.
Three
Oh,
process
sorry.
arrive at time t equal to 0. Therefore, what is the turnaround time of process B?
More than 100.
More than 100, right? That is the problem with this approach. FIFO, first in first out. If you stuck behind if the process stuck behind with a long fat process, therefore the turnaround time of the process B will be very, very high. Okay, all right.
Yes, sir.
Yes, sir.
Okay, good. So how we can overcome this problem? How we can fix this problem?
Doing small
Allotting a
pieces.
limited time to each process for execution.
Okay, good, good. So can you tell me the name of the algorithm? Okay, fine. So we know that FIFO have a problem of turnaround time, right? So to overcome this, we have an algorithm called shortest job first. Okay, again you have two diagram here, two figures. Just have a look, then we'll explain on this. First, look at figure 7.3. What do you mean by shortest job first? All three processes arrive together in the system. Okay, we have process A, process B, process C, all arrive to the system at the same time together. Now, it makes sense to finish the process B and process C first. Why?
Because they take a shorter time to execute when
Good.
compared to A.
Good, good. Now let us assume that the process B need 10 milliseconds to complete the execution, and then the process C need 10 milliseconds to complete the execution. The process A need 100 milliseconds to complete the execution of instruction. Now, when all this process comes to the system at the same time, now this SJF checks the shortest time process, and that will be executed first. Okay. You understand this?
Yes, sir.
Yes, sir.
Good. Now, what is the problem with this approach? What is the problem with SJF? What do you mean by non-preemptive? Of course, FIFO is also a non-preemptive. What do you mean by non-preemptive? Only then we can understand rest of the part. Can you tell me what is non-preemptive?
So the process which is going to take lesser time will stuck to waiting for the long process.
Okay, I
The
think
switch between process happens only if it's blocked or terminated.
okay, 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 fine. I think I have to give more explanation on preemptive and non-preemptive. Now, see, you have process A, process B, process C. Okay. Now, process A need 120 milliseconds. The process B need 8 milliseconds. The process C need 10 milliseconds. Are you able to see this figure on the screen?
Yes, sir.
Okay. Now, in the case of preemptive scheduling, okay. Now, let's say that all this process A, B, C arrived at the same time, t equal to 0. In the case of preemptive, okay. Yeah, first let me complete non-preemptive. In the case of non-preemptive, which process comes to the system at first?
A.
So
Process A. How much time is required for the process A to complete?
120 milli.
120 milliseconds.
120. Okay. In the case of non-preemptive, the CPU will provide complete 150 millisecond in a continuous stretch. 120 milliseconds will be given to the process A only when the process A completes the execution. Then there will be a contact switch from the process A to process B. Okay, this is non-preemptive. You understand?
Yes, sir.
Yes, sir.
Sir, in case if a process A is blocked or terminated also, it will switch to process B, right? Or else would it wait to the process to be ready?
No, in the case of non-preemptive, the CPU will be completely with the process A. Only when it completes the execution, only then it will move to the next process.
Yes, okay.
Okay, even it requested for some services. That's how the algorithm is designed. In the case of non-preemptive, the CPU cannot move. The operating system will not make a context switch. It makes the process A to complete, only then it moves to the other process. Okay. All right. Is that okay? Fine. So what is non-preemptive then? What is preemptive then? What is preemptive?
So does it mean that the task can get terminated in between if it takes too long?
Good. Now let's say that you have three process A, B, C comes to the system at time t equal to 0. Now when the CPU execute process A, uh, when the CPU executing process A, then the process B need only 8 milliseconds, but the process A need 120 milliseconds. Now what operating system does here is, okay, the operating system decides to switch to the process A. The CPU will stop the execution of process A and it will move to the process B for the execution. Okay.
Yes, sir.
Yeah, so that is the difference between preemptive and non-preemptive. Fine. Okay, so in the case of shortest job first, uh, so we know that from the figure 7.3, the process B and C need only 10 milliseconds. Therefore, that will be executed first, and then the process A will be executed at last because the process A need more amount of time, right? But the problem with SJFS is non-preemptive. Now, can you tell me from the figure 7.4 what happens in figure 7.4? What is non-preemptive?
A task?
Sir, if the process that are short jobs arrives late or arrives before the long after the long process, then only after the A will get executed, then only they will get executed.
Good. That is what the non-preemptive is, right? Now look at the figure 7.4. Now the CPU is executing the process A, the fat process, which need more time, right? When the CPU executes the process A at time 10, okay, at time 10, B and C arrived to the system. Okay, B and C arrive to the system when the CPU is executing the process A. But the process B and C need only 10 milliseconds. Need only 10 milliseconds to complete the execution. But what SJF does, it will it will not stop the execution of process A. It will continue. It makes sure that the process A completes the execution of all the instruction. Only then B and C will be scheduled for the execution. Okay. All right.
Yes, sir.
Good. Now how we can provide a solution for this? So what happens to turnaround time of process B? High or less?
High, sir.
Good. What about the turnaround time of process C?
High.
Hi,
Good.
sir.
High. Now what is your optimization goal? You want an high turnaround time or less turnaround time?
Less turnaround
Less.
time.
So how we can provide a solution for this? Okay,
Minimize the average time of each.
good. Now for that we have another variant. Okay, we have another variant of SJF that is called as shortest time to completion first. Okay. Okay, in the case of SJF, this algorithm is non-preemptive mode. So in order to provide a solution for this problem, we have another variant of SJF algorithm which is called as shortest time to completion first, and this algorithm is also called as SRTF. What do you mean by this? What is S?
Shortest remaining time first.
Good. Shortest remaining time first. Good. Now from the figure, can you understand now? Now this is
Yes,
preemptive
sir.
scheduler. This is preemptive scheduler. Okay. So now at time t equal to 0, which process comes to the system?
A.
Good. Let's say that the process A need total of okay, approximately 110 milliseconds. Okay, the process A need of 110 milliseconds. When it completes the execution for 10 milliseconds, when process A completes the execution for 10 milliseconds, at time t equal to 10, we have process B and C arrive to the system, and process B need 10 milliseconds and process C need 10 milliseconds. Now what happens to the execution of process A? It stopped or continuing?
It gets stopped and B and C execute.
Stop.
Good. Now the operating system decides to switch from the process A to the process B because the process B need only less uh, time for the completion. That is shortest job. The process B and C is the shortest job to complete. Therefore, the operating system makes a contact switch from the process A to B. So B will be run for 10 milliseconds and then it will move to process C. It will be executed for next 10 milliseconds and only then the CPU will come back to the process A to execute the remaining instructions and for remaining times. Okay.
Sir, here in the duration of 0 to 10, some part of A would be executed, right, already before B and C
Yes, yes,
arrive.
yes.
So
Yeah,
that part would be stored in the program counter, right? After C execute, then it restores the old PC values and then the remaining part executes.
exactly. Same concept here, the contact switch. So at time t equal to 10, the operating system stops the execution of process A. Now, when it stops, what happens? In the kernel stack, what we store?
Old PC values of A.
Yeah, the program A may have multiple line of instruction. Say you have 1000 line of instruction for the process A. For 10 milliseconds, it has executed 150 line. From 0 to 150 it has executed. So at 150th line it has stopped the execution. Operating system stopped the execution. Therefore, that PC value, the 150th line PC value, will be stored in the kernel stack.
Yes, sir.
Right? And operating system decides the process A, you need so much of time to complete the execution, but process B and C only need shortest time. So first let me go there and let me complete those, then I'll come back to you. Right? That's how the operating system time shares the CPU.
Sir, here we said that B and C have same time to execute, right? They
Yeah,
are arriving at same time and the execution time is also same. But what if they also differ by in
good.
milliseconds?
Good. Let's say that the process B need 8 millisecond and process C need 10 millisecond. Now both arrive at the same time. Now operating system sees out of these two, which has the shortest job?
Process B.
So B will be executed first and then C will be executed.
Okay, sir.
Okay, good. Fine. So the next algorithm is round robin algorithm. Okay. Uh, so everyone okay with this?
So
Okay, so the next
Yes, sir.
simple, okay, good. The next simple scheduling policy is called round robin, RR scheduling algorithm, right? Now, how this works? Okay, fine. Uh, Let us try to understand the disadvantages of SJF. Okay, now in the case of SJF, is that uh, good for response time or bad for response time?
Bad.
I I mean SJF, okay, not the variant, not STCF. I ask you only SJF. Is this is good for response time or bad for response time?
So bad.
What is response time?
So the time between it arrives and its first scheduling.
Good. Now in this figure, at what time B and C is arrived?
10 milliseconds.
10 milli.
At 10 millisecond, both the process arrived. But what is the first time it gets scheduled?
100.
100. So do you think this is good for it is good response time or bad response time?
I think bad because it's like 90 seconds gap between these.
Yeah, it's a bad response time, right? See, what is response time first? The time of arrival and first scheduled by the CPU. Time of arrival and first scheduled at first time scheduled, that is called response time. But here the process B and C arrived at time 10, but it is first scheduled at time 100. So we have a bad response time here. So how we can overcome this? Look at figure 7.7. How we can overcome this? How we
Round
can,
robin by.
yeah, we have a policy like round robin. Now what we do here, we put all the list of process in a queue. Okay. Okay. Let's say that you have process P1. I think someone is unmuted. Okay. Good. Uh, in the case of round robin, you have a long queue. In the long queue, we keep all the list of process. We keep process A, process B, process C, process D, and so on. Okay, we keep all the list of process in a queue, and what we do, we execute process A for some time, and then we execute process B for some time, and then process C, and so on. And then you execute process D, and again you come back to the process A. You understand this?
Excuse me, sir.
Yeah.
So then in this situation, sir, we are switching multiple times. So then it will take a lot of amount of time.
Exactly. That is what your bullet point second says, right? So before that, let me tell you what is the mechanism of round robin. So look at the figure 7.7. First, you have a list of all the process that will be kept in a queue. Okay, in a queue you have a process A, B, C. The process A is executed for some milliseconds, and then it move to process B. Process B will be executed for some time, and then we move to process C. C will be executed for some time, and then we come back to the process A. Process A will be executed for some time. So when this happens, so run for fixed every process run for fixed time quantum. Look at the first bullet point. Every process will run for fixed time quantum. Now this time quantum can be 5 milliseconds, can be 10 milliseconds, and so on. The time cannot be really small. You cannot run the process only for 1 milliseconds. Why? We cannot run a process for a microseconds. Why?
Because context switch also takes some time. So
yeah, because that is what happens in round robin, right? You execute process A for certain milliseconds. Okay, let's say that you have 10 milliseconds. For 10 milliseconds, you run process A, and then you move to process B, execute execute for excuse me, execute for next 10 milliseconds, and then move to process C, execute for 10 milliseconds. Now what will happen if this quantum time is 1 millisecond? What will happen?
So a lot of switching would happen.
Lot of switch from process A to process B. You will have multiple rounds of this, multiple switch, multiple round, right? So every time you switch, we also need some time for to perform the mechanism of contact switch. So your turnaround time will be very bad for this, right? So once you switch, you want to run the process for the reasonable amount of time. Okay. Okay. All right.
Yes, sir.
Now, this round robin is a preemptive or non-preemptive?
Preemptive.
Why you call it as preemptive?
So because the tasks get they get stopped in between to execute another task.
Okay, let's say that
Yes.
your quantum time here is 10 for this example. Okay, your quantum time is 10, and your process A need 20 milliseconds to complete the execution completely. Process A need only 20 milliseconds to execute the instructions completely. Now, because your quantum time is 10, in the first round, the process A will be executed for how much time? In the first round, the process A will be executed for how much time?
10.
10 milliseconds, right? And then we make a context switch to B. Process B will be executed for 10 milliseconds, and then process C will be executed for 10 milliseconds. And again, we come back to the process A to execute the remaining 10 milliseconds. So this is a preemptive, right? And this algorithm is good for response time. Why is that? Why it is good for response time? What is response time?
Because it's a, so the response time is the time between its arrival and the first schedule.
Good. Now, from the figure 7.7, can you tell me that whether RR is good for response time?
Yes, sir.
Because process A, process B, process C, those got first scheduling in every 10 milliseconds. Okay, so RR has good response time, and this also a fairness, right? Every process get equal amount of time for the execution. Yes.
Yes,
All right.
sir.
Yeah, and the last topic is bad for turnaround time. RR is bad for turnaround time. Why? If you're, let's say that the process A need 20 milliseconds, the process B need uh, 30 milliseconds, and the process C need 10 milliseconds. Now your quantum time is 2. Your quantum time is 2. Now what will happen to the turnaround time of process A? Will be high or less?
Hi.
Why? Because every 2 seconds we make a contact switch. For first 2 seconds, process A will be executed and then move to process B. So in the first round, after execution of 2 milliseconds, what is the remaining time of process A?
18.
18. So it has to, the process A has to wait the B to execute for 2 milliseconds and C to execute for 2 milliseconds. And then the CPU comes to the process A. And in the next round, it will execute for 2 milliseconds. So the remaining time is 16. Again, the process A have to wait for next 2 milliseconds for process B and 2 milliseconds for process C. Now, do you think the process A turnaround time is high or less? High or less?
Hi, sir.
High, right? Because the time arrive to the system and time it get completed. So it has to wait for every 4 milliseconds to get the turn of CPU for the execution, right? Okay, so let me stop here. Do you have any questions to ask?
No, I have a small question regarding the DA.
Yeah, please go ahead.
So in the theory DA, do we have to type it, right? We have to type it, right?
No. We have to write it. Okay, so please, I request everyone to draw the architecture in a neat way. All right. Okay.
So is this for the theory DA?
Yeah, this is only for theory DA. For lab DA, you can submit the soft copy.
Oh, like have you given the questions already, or you gonna give it?
I have given already. I think we have discussed in last class. Can you please confirm in your VTOP?
Okay, so
Yes, sir, it's there. It's in that section, the course-based part.
Yeah. Yes. Yeah. Okay. Don't worry. You have only 4 questions. The first question could be that the architecture, right? I think you'll have maximum of 5 questions.
Sir, it says the form is not
So
correctly
isn't
accepting.
Yes,
responses.
Sorry.
The form
The
isn't
form is
accepting responses.
Hmm. One second. Sorry for taking your time. Okay. Yeah. Okay. Sorry. Yeah, I think you can. Yeah, you can do it now. Please let me know. Able to do now?
Yes, sir.
Good. Thank you. Raghav, you can see the DA1. You have 4 questions.
Yes, sir.
Here, the computer system organization. You know that, right? You have CPU, you
Yes,
have
sir.
IO devices, you have OS. How this are interconnected? What is the advantages and disadvantages? I think uh, maybe before Cat 1, let us try to discuss this. And
Yes, sir.
then the question 3 is the operating system structures like monolithic, layered, modular, and microkernel. All these are a kind of architecture. We do not have much to discuss, like a trap instruction or context switch. We have to read everything from the architecture, right? So I just need to tell what we have in the architecture. Right? So that is the reason why I have not done it in the couple of classes. So you will feel very, uh, you will feel that the operating system is very theoretical, right? So maybe
Yes, sir.
we'll do it. We'll do this before a cat one, and
All right, sir.
good. And the last is a system call.
Okay, sir.
Fine. So I request for DA1 for theory, you do it in the handwritten. Please make sure that you draw good architecture and then you explain of that. And for lab DA, you can submit in a Word PDF file. Okay.
All right,
All
sir.
right.
Thank you.
Good. Thank you.
Thank you, sir. Thank you,
Yeah.
sir.
Thank you very much. Can we end for the day?
Yes, sir.
Yes.